Welcome to today's Explainer. We're diving into something that honestly sounds a bit like it belongs in a gritty spy thriller, but it's actually a massive cornerstone of modern civil engineering. It's called the cut-throat flume. Now, behind that incredibly dramatic name is a remarkably elegant tool. Engineers use it to measure open-channel water flow, which is absolutely essential for managing global agriculture and irrigation. Today, we're going to take a close look at experiment number 6 from our Open Channel Flow Laboratory series. We'll journey through exactly how this device works, why it was even invented in the first place, and how the math we do on paper ultimately translates into life-giving water for crops all around the world. Okay, so here's our roadmap for today. We'll meet the cut-throat flume, explore its anatomy and flow theory, and then unpack the math behind the flow. After that, we'll get into setting up the experiment, walk through the step-by-step procedure, and finally look at submergence and its real-world impact.
All right, part 1. Meet the cut-throat flume. What is it, and why do we use it? So we're starting off by trying to solve a pretty major problem in open-channel hydraulics.
When you've got water flowing through an irrigation canal, you absolutely have to know how much water is moving at any given second, right? Without that, efficient distribution is just a guessing game. So, how do you measure a flowing river or canal without stopping it? That's where this device comes in. And that dramatic name? It actually comes from a very simple design feature. It's a flow measuring device with a completely flat bottom, straight vertical walls, and, here's the kicker, a zero-length throat section. Because it literally has no elongated throat connecting its entrance and exit, engineers just went ahead and gave it that unforgettable name, the cut-throat flume.
And this brilliantly illustrates why it was invented. You see, prior to this design, engineers frequently used something called a partial flume. The partial flume is fantastic, but it has a major drawback: complicated fabrication. It requires these custom downward and upward sloping sections that have to be built perfectly to spec. The cut-throat flume was a direct attempt to fix that by vastly simplifying the construction. By just sticking to a flat bottom and vertical walls, it becomes highly economical and incredibly easy to build, especially for small, straight irrigation channels. It's a real game changer. Moving right along to part 2, anatomy and flow theory. Inside the flume. Let's transition from the history into the actual physical design.
Get this, here is an incredible engineering shortcut. The angle of divergence, which is where the flume widens out, and the angle of convergence, where it narrows in, remain exactly the same for all sizes. Since the angles never change, engineers can easily scale the capacity of the flume simply by moving those flat vertical walls in or out. Whether you're using a tiny 45-centimeter flume or a massive 3-meter structure, the fundamental geometry is perfectly identical. Let's anchor this in reality and look at our laboratory setup. Imagine tracing the water's journey. It starts at the inflow pump, travels down the rectangular channel, enters the converging section of the cut-throat flume, squeezes through that zero-length throat, expands in the diverging section, and then flows right on out past the tailgate. The pure simplicity of that flat bottom means there are no complex slopes for the water to navigate. It's just a pure geometric squeeze and release. Next up, part 3, the math behind the flow, calculating discharge. The crucial point here is figuring out exactly how much water is moving through that geometric squeeze.
Okay, I know looking at variables can be a lot, but don't let this intimidate you. These just represent physical realities we can easily measure. We're looking for theoretical discharge, or QTF. To get that, we need a free flow coefficient, C. We take that C and multiply it by our upstream flow depth, H, raised to a flow exponent, n. Now to find that C in the first place, we take a length coefficient, k, and multiply it by our actual throat width, w, raised to the power of 1.025. It sounds like a mouthful, but the physical dimensions of the flume are actually doing most of the heavy lifting for us here.
And here's the absolute best part. To find those complex constants like k and n, we don't have to guess or do crazy calculus, we just read them directly off specialized engineering charts. By taking our specific flume length on the bottom axis, we trace a line straight up to intersect the curves. This lets us pinpoint our flume length coefficient, our flow exponent, and something called transition submergence, all in one quick glance.
All right, part 4, setting up the experiment, the lab environment. We've got the theory, we've got the flume. Now let's build out actual experiment number 6. So for our specific lab setup, we're using a flume length, L, of exactly 1.5 meters, and a very narrow throat width, W, of 0.0762 meters. Using that 1.5 meter length on the chart we just talked about, we pull our constants. We get a value of 2.8 for K, 1.69 for our exponent n, and 72 for our transition submergence limit, St. We also independently measured our actual discharge flowing from the pump, our QA, which sits at 0.0132 cubic meters per second. Keep that number in mind. That actual discharge is highly important. It's our ultimate answer key that we'll use to prove our flume's accuracy at the end.
Part 5, step-by-step procedure, running the numbers. Grab your notebook because this is how the pros actually run the math on the bench. Step 1, we measure the water depth upstream from the flume throat. This gives us our Ha value, which in our demo came out to 0.203 meters. Step 2, as we just did, we grab our chart constants K and N. Moving on to Step 3, we crunch the free flow coefficient, C, by multiplying K by our throat width raised to 1.025. And finally, Step 4, we plug C, Ha, and N into our main equation to reveal our theoretical discharge, QTF. Following those exact steps, our theoretical calculation came out to 0.0135 cubic meters per second.
And now, the absolute moment of truth. When we divide our actual measured discharge of 0.0132 by our mathematically derived theoretical discharge of 0.0135, we get a coefficient of discharge of exactly 0.98. In the engineering world, a coefficient that close to a perfect 1.0 is incredible. It proves this simple, flat-bottom flume is practically flawless at calculating flow rate. No way around it, the math works.
Just to be totally sure this wasn't a fluke, we verify our work by plotting the data on a log-log graph. Because the discharge equation involves exponents, taking the logarithm of both sides magically turns it into a classic straight line equation. By graphing our actual discharge against our upstream depth on this log-log paper, the slope of the resulting straight line directly gives us our flow exponent n. It's a beautiful, highly visual way to double-check our math and confirm those chart values. Finally, Part 6, Submergence and Real-World Impact. When flow gets complicated, because let's face it, the real world rarely stays in perfect laboratory conditions. What happens when water exiting the flume starts backing up? Maybe there's debris or a closed gate further down the canal. This brings us to a critical check, the submergence ratio. This is simply the downstream water depth, HB, divided by the upstream water depth, HA. We absolutely must check this, because if the downstream depth gets too high, it creates back pressure. If this ratio exceeds the transition submergence limit we pulled from our chart, the flume is considered submerged, and all of our beautiful, simple, free-flow math completely falls apart. Let's look at our demo data to make sure we were safe. Our downstream depth was measured at 0.139 meters. We divide that by our upstream depth of 0.203 meters, multiply by 100, and we get a submergence ratio of 68.48%. Remember our transition limit was 72? Because 68.48 is safely below 72, we successfully confirmed that we maintained perfect, uninhibited free flow the entire time. As we wrap up this explainer, I'll leave you with this thought to ponder. We just saw how completely flat walls and a little bit of geometry can calculate water flow to a 98% accuracy. Without brilliant, cost-effective simplifications like the cutthroat flume acting as silent sentinels in small irrigation channels around the planet, accurately distributing life-giving water to the world's crops would be practically impossible. So the next time you see a farm, ask yourself, how much invisible math is keeping those plants alive? Thanks for joining me on this deep dive, and keep questioning how the world around you is measured.